All right, happy Thursday. Thursday, week 3. It's going, you guys are doing great. I love chapter 4 stuff. Chapter 4 stuff is going to feel like it doesn't really fit in with everything else, but it's really important, and most people use the chapter 4 stuff on their final project. So pay attention, obviously. And this will be on the test. This is the last of the new material that'll be on the test. So chapters 1 through 4. So after tonight, you will have everything you need to work on the test review and to start studying for the test. Lab 3, we will go over Lab 3 afterwards. Once you get your data, Lab 3 is pretty quick, but your Lab 3 uses two different variables. Usually they're on the same study, so you think they're probably correlated. So you get two variables you think are correlated with each other, and that 20 data values each one. And we're going to do some fun stuff there with Excel. Had something else. It's gone.
Did you
Whatever.
say there was a test review?
There is a test review. It's in the week 3 materials. Just a second, I'll get there.
Oh, okay. I don't
Yeah,
even think.
it's not an assignment. It's just a review. It's not something you need to turn in. So if you go to week 3, um, so right here, chapter 3, continue, and section 4.1, down here at the bottom, test 1 reviews right there.
Thank you.
You're welcome. See, I'm glad I said that. Perfect. We're also going to learn some fancy schmancy calculator functions today. I know the calculator has been a little rough. The more you practice it, the better you're going to get. Write down everything. Like write down, to find standard deviation, mean, median, Q1 and Q3. Write down how to get there. Write down how to get to the lists. One variable statistics. And then tonight we're going to learn linreg. And so write it all down, write the steps to get there and all of that. So I highly recommend writing stuff down. Make some lists. All right. So we're going to be looking at scatter diagrams today. We're going to be interpreting them and drawing them. You will not have to draw any for the test or I don't think even for your homework, but we're going to draw one. And we're going to talk about something called a correlation coefficient. And we're going to talk about whether a linear relationship exists and the difference between one brief slide about correlation and causation. And then we're going to find the least squared regression line and go over lab 3. So that's tonight, and it'll be fun. I mean, it'll be fun for me anyway. I love this stuff. So hopefully it'll be fun for you as well. I do my best. I try to make it fun, but it is math after all. It's kind of funny. I ran into a former student today, and she's like, Miss Kleiss, I really miss you, but I don't miss your math. And it's okay. It's okay. It is okay to like me and hate my math. As long as you're not hating me and liking my math, that would make me sad. So, all right, let's go on. Okay, so here is our vocabulary. So the response variable is like the dependent variable. So usually it would be the y in your y equals mx plus b. It would be the y. It is the vertical axis. So it is a dependent variable because it requires the first variable to make it happen. So for example, if we're talking about miles per hour, if no hours pass, you don't go anywhere. Therefore, hours would be my response variable. I mean, miles would be my response variable, and hours is my explanatory or my independent variable. So the one that is caused to happen or caused to change is your dependent variable. It's not always going to be clear. So there's not always one that is necessarily has to be the dependent variable and the other one has to be the independent variable. That's the thing with stats, is sometimes one of the things doesn't cause the other thing to happen, but we just have to choose one or the other. And you'll see an example of that with my lab. My lab is one where it doesn't really matter. So explanatory or the predictor variable, this is the one that's driving the bus. This is the one that's causing things to happen. So this is usually the x value in y equals mx plus b. So miles per hour, once again, and hours have to pass in order to go any miles. So hours would be your independent variable, your explanatory slash predictor variable, and then miles is the response. The scatter diagram, you've all seen a scatter plot. It's all the dots on the graph, and it shows the relationship between two quantitative variables. This is going to help us to determine if there really is a relationship, a linear relationship between two variables. We're going to be looking at a scatter diagram. So that's our vocabulary for this. That's most of the vocabulary. Going to get a couple more little tidbits. And then, yeah, this is so much fun. I love it. Okay, sorry, I just get excited. This is one of my favorites. I think I say that every time. All right. So this is a step based on a study for drilling rock. So what they determined was how long does it take to drill 5 feet of rock, based on how deep we are when we start drilling. So for example, when I'm 120 feet down, when I'm 120 feet in the hole, it takes me 7.47 minutes to drill 5 feet. So I don't know, I'm sure it has to do, geologists would know much better than I am about different types of rocks at different depths, and I'm sure it all has stuff to do with that. But, so at 35 feet, it only took me 5.88 minutes to drill 5 feet. So our explanatory variable, the variable that makes something happen. So this right here would be our explanatory. Well, I guess I need a pen on. This would be the explanatory. And then this is the response. If I don't start drilling, then there's no time to happen. If we don't have a time to drill 5 feet, if I don't start drilling. So the time to drill is dependent on how the depth at which I started drilling. Okay. Move on. So this is my scatter plot right here. So if you look at my scatter plot, you can kind of see, I'm just going to draw a line through it. You can kind of see that as my drilling depth gets deeper, it's going to take me longer to drill. Now, not every time, like this one right here. That one we drilled pretty fast, but for the most part, most of them, I mean, you can tell it kind of has a positive slope there. It is going up. As the depth gets deeper, the time is getting longer. You can see that there is a trend there. Okay. So we're going to actually create our own scatter plot. So a golf pro wanted to investigate the relationship between club head speed of the golf club, so how fast we swing the golf club, and the distance the ball is going to travel. So he had to try to make it so that that we don't that there's not so many other variables in play. So he knows that if we use like weather conditions, if we use a different type of club, if the ball type is different, if there's a different golfer, then it's gonna cause changes. It's gonna cause it to be different. So what they used one person, they used one single model of club, they used one type of ball, they had a 70-degree day with no wind. So they wanted to get it so that our only variable is how fast the club head is moving. So they did the best they can with that. So we're going to draw a scatter diagram. So here's our data. And we're just going to plot the dots, our XY variables. So the club head speed is our X value because if the club head doesn't move, the ball doesn't move. So the distance in yards will be my response variable because it's responding to how fast the club head speed is. All right, so I have 100, 257, 102, 264. And we're just kind of estimating because we don't have like the exact spots. 101, 266, 5. Another 100, 263, 99, 258. About there. 105, 275. All right. So as you can see here, once again, you can see as the club head is going faster, my speed is, or my distance is also going farther. I mean, it makes sense. Logically, it makes sense. Of course, if I swing the club head faster, then the ball is going to fly farther. It just makes sense. I mean, it's kind of silly to even think that it wouldn't. So this is it. This is my scatter plot. We're going to do so much fun stuff with this after. All right, move on.
That's
Okay.
what I was gonna ask you about our lab, because you want us to get two correlated, things, but there's so many um different variables that can go into so many different things. So
Mhm.
we're not focusing on all the things like that. We just are trying to see the graph of it basically.
Yeah, you're just
Yep.
going to choose two that you think are correlated, and they may not be. So many times people will choose two variables that they think are correlated and then they end up not being correlated, but that's okay. I
Okay.
mean, that's what we're looking for. We're trying to determine whether or not they are. So just find two things. I mean, it's really easy to go on like the Weather Channel and look at 20 different days and look at like temperature and wind speed or
I did,
something.
sorry, I did the year of all the Toyota 4Runners and how much they're going for each year,
Okay,
like the price wise.
sure.
Like I went into the same like Kelly Blue Book and checked on every single year and how it went up or down, which is weird because some of the older versions are more expensive. And
It's
it's like,
because after as when a car gets to be a certain age, then it starts being like a classic. And
yeah,
so you end up, yeah, it ends up being pretty weird. But I love that. I think that's great data. Yeah.
okay.
And I mean, I like using sports because there's so much data out there. So usually my examples end up being sports, not the ones I use on my labs, but the ones I recommend to people because sports is quick and easy. You can jump. Maybe we've got the Super Bowl coming up, so it's like I automatically think football, but you could just jump on and you could say like, weight versus yards rushed or whatever, or you could even look at the team's budget versus how many games they won this year. There's so much you could do.
Okay. That's
And,
cool.
I'm a sports person anyway. I love sports, so I automatically go there. But there's just so many things. You can go on the US Census website and you could find all sorts of data for and pick 20 states and pick two different types of data for 20 different states. There's so much out there. So yeah. How
I
do you
have a question for the
Yes.
credibility of like finding your sources because I did like temperature versus the number of sales and ice creams.
Uh-huh.
And to do that, I just like searched that in on Google and then searched images to find like the X and Y values. And that was like off of a website that I don't know of. Does that still count? Like I don't know its credibility, but
The labs, I don't care. Because for the labs, all we're really just using the Excel tools. So I don't care a whole lot about how good your data is. For your final project, I would prefer you have better data. But most of the time, people collect their own for final projects, which you don't have to. But they'll. So for the labs, I don't care if your data is credible.
okay, thank you.
You're welcome. Because really, the labs aren't about data collection. The labs are about using the Excel tools. The final is about data collection and using the tools and using all of the stuff that you've learned this term, which nobody freak out about the final project yet because it's only week 3. It's not due till week 11. So don't freak out yet. I just want to have it in your head so you can just start thinking of what am I interested in? What might be fun and start just thinking about things. So there you go. All right, moving on. Okay. So in this class, we're specifically looking at linear relations. We are not looking at any other type of relations. We're looking at linear. So, um, if you look at these first two, A and B, you can see very clearly that these are linear. I can draw a line through them and it aligns pretty closely with what's happening with the data. That one is a pretty great positive linear relationship. It looks very linear. Same thing with B. This is a negative linear relation, but it is a line. I mean, it's pretty clearly you can see that it is as X is getting bigger, Y is getting smaller. It's pretty clear. You can see that that's linear. This one right here, there's a relation there. This is quadratic. It's a parabola. So there's a relation there, but it's not linear. So there's no linear relation here. It is very much nonlinear. This one, the letter D, that one is cubic. Don't worry, you don't need to remember that that's quadratic and that's cubic. You don't need to remember that. But it is a cube. It is cubic. It is not linear though. I can't just draw a nice pretty line through it and it's going to get through most of the data. That is not linear. There is a relation there, but it's cubic. It is not linear. The last one, letter E, it is completely random. It is not linear. It's nothing. It is no relation at all. So there's just nothing there. So just because there's not a linear relation doesn't mean there's not a relation at all. It's just not linear. So, but these two are linear. All right. So a positive association, if they're positively associated, if they have a positive slope. So if as my X is getting bigger, my Y is also getting bigger, that would be a positive association. For a negative association, if as my X is getting bigger, my Y is getting smaller, then that is a negative association. So think about it as positive association, it is going uphill from left to right. Negative association, it is going downhill from left to right. Uphill from left to right. Downhill from left to right. To me, that's even better way to remember it than saying if as X gets bigger, Y gets smaller. For some reason, the uphill and downhill helps me. All right, any questions so far? Are we doing okay? I'm excited about using the calculator. So I don't know about y'all, but I'm excited about using the calculator. All right. You do not ever have to use this formula. Don't let it get mad at, don't get mad at it. This formula is big, it's ugly. You don't ever have to do it in by hand or even in your calculator. We're just going to look at this and say, okay, that's pretty and leave it alone. So the linear correlation coefficient, or just the correlation coefficient, it tells you the strength and the direction of the linear relationship between the two variables. It's going to tell you how strong of a linear relationship we have. So if I was using a population correlation coefficient, I would use the nice Greek letter because remember, the population gets fancy, rho, but we almost never use population. 99.9% of the time, we use the sample. So we're going to throw rho away and we're just going to use R. Remember, samples don't get pretty letters. So R represents the sample correlation coefficient. I frequently will just call it an R value. Even though it is a correlation coefficient, it is a mouthful to say that over and over and over again. So we'll just call it an R value. R value is the correlation coefficient. And in your calculator, it'll be an R value. But you will never have to do this formula. I will tell you what it is though. So it takes the standard deviation of so actually this is all of the z-scores of every x value, that's what that is, added together. This is all of the z-scores of all the y values added together, and then but we're multiplying them. So actually it'd be like take the z of x1 times the z of y1 plus the z of x2 times the z-score of y2, all the way through all your data values. You're multiplying them together and adding them together, then dividing by n minus 1. Don't ever do this in person. Please do not. I mean, if you really want to like get committed to a mental institution or something, do this formula. That's basically what I'm telling you. So don't do it. I did have one person one time use this as their hand calculated formula on their final project. And I just don't even know why. Why would you do that? It's ugly. Okay, moving on. I'm gonna move right past this. You tried it and you cried. Why did you do that? Yeah, see? It makes people cry. Don't do it. Okay, now this is a whole lot of words. It's a whole lot of words. So I'm going to try to make this not so ugly because it's a whole lot of words. Okay, linear correlation coefficient is going to be between -1 and 1, and it says negative and it says inclusive because you can have a perfect 1 and you can have a perfect -1, but it can follow the entire interval between -1 and 1. You will never have an R value greater than 1. You'll never have one less than -1. So it'll be in between those two. If you get a +1 correlation coefficient, it is a perfect line. It is a perfect linear relation, positive. If you get a -1, it is a perfect negative linear relation. It's a perfect line. So the closer you get to +1 and the closer you get to -1, the stronger the linear relation is. So if I had a linear relation, a correlation coefficient of like 0.98, that is almost a perfect positive linear relation. Or if I had -0.96, that is really great negative linear relation. I'm going to give you like my rule of thumb, but as I've said, statisticians don't deal in absolutes, so there's a little bit of wiggle room there. So it really depends on how important it is that you have a nice positive linear relation. Like if I'm building a space shuttle, I would say that even probably 0.95 would be bad. But if I'm putting a garden in my backyard, 0.85 is probably perfectly good. All right, so next, if we're really close to 0, then there's little or no evidence that there's a linear relation. So close to 0 basically just means no linear relation. There could be a relation, just not linear relation. That quadratic we saw would probably be close to 0, but it won't be linear. It is unitless. We don't say 0.98 feet. There's no units. And it is also not resistant. So it's kind of like mean and standard deviation. One outlier can drag it. So the R value can get dragged real easily by outliers. So that's what it means by not resistant. So I'm not going to ask you to recount these facts to me, but you're going to kind of use it. And without all of these words, you'll be fine. All right. So here we go. So letter A is a perfect positive linear relation. And B is about 0.9, the R value. So it is actually pretty good. That's a pretty strong linear relation. Now letter C, it says it's 0.4, but I would say that C is probably closer to about 0.6. It's 0.4 would be more scattered than that. So that's about a 0.6, I would say. Letter D is a perfect negative linear relation. It has an R value of -1. And then E is a very strong negative, so it's about 0.9, -0.9. And letter F, to me, it doesn't look like 0.4. I would say that it's probably about -0.55 approximately. Letter G is pretty darn close to 0. It might be like 0.15 or something, but it's really close to 0. And as I said before, H is also really close to 0. It's a nice, pretty relation, but it's not linear, and it's a quadratic. So it's close to zero, but there is a relation there. It's just not linear. Questions on these?
So if
Is
it goes up,
Go
is it
ahead.
like positive?
What was that?
So if like it goes like if it's like graphed and you can put like the little if you can put a little line between it, it's a positive.
So it's if it goes uphill, so see this goes uphill, it's positive. And this one this goes downhill, so that one's negative.
Okay.
Yeah.
Okay, got it. Okay.
All right. Hannah, did you have a question?
No, Dominic did.
Okay.
Yeah, I had one real quick. Both G and H are non-linear and they're close to zero, but like are one of the two closer to zero, or are they both just
It would be really hard to say. I would say G is probably closer to zero because I could almost get, because see this part right here, I can kind of almost get a line.
okay?
There's really no way to get any kind of line on G. So I would say H is probably farther away from zero. So G is probably closer to zero than H. But I mean, it's kind of hard to say, but that would be my guess. All right.
Thank you.
You're welcome. And it's good to see your face, Tom. It's been years.
Yeah, I was wondering if you recognize me in this class. It's nice to see you again too.
Definitely recognize you. All right. Let's move on. Okay. So now we are going to determine the linear correlation coefficient. I need you all to do something with your calculators first. We're going to use the fancy schmancies. And wow, that's not where we are. Okay. So we're going to use the fancy schmancies. So most calculators probably are not set up to get an R value. So we're going to go into our calculator and we're going to do a setting that is going to make sure that the R value shows up. So even if your setting is already turned on, it's not going to hurt to do this. So what I want you to do is click the second button and then 0. So hit second 0 and you're going to get a catalog. So everybody hit second 0, you'll get a catalog. Scroll way down till you see diagnostic on. Uh-oh, went too far. Go to diagnostic on. It's all alphabetical. Once you find diagnostic on, you're going to hit enter and then hit enter again. And when it says done, you're set up. You only have to do this one time. And once that's turned on, it's going to be turned on until somebody resets the calculator or turns it off. All right. Are we all there? We're good? Okay. Now we're going to go into, okay, just a second here because I need the data. So, okay. So we're going to go into stat because we want to go into our lists. So hit stat and edit and get to our lists. I have all these crazy ones here. I'm going to clear out list 1 and list 2 because we need both of them. So highlight L1, hit clear, enter. Then highlight L2, hit clear, enter.
Can you repeat that
Okay. From where? From which spot?
from the list? I mean, I have an 83, so I don't know if that's part of the issue.
Does it not allow you to highlight them? You're going to hit stat. You hit stat and then go into edit and then you highlight L1. So hit the arrow up until L1 is highlighted and hit clear, enter. Then go over with the arrows again, push up arrow to highlight L2, hit clear, enter. My 83 ran
I
out.
got it. Thank you.
My 83 ran out of batteries. Otherwise, I would work along, have mine out. But thankfully, this one doesn't need batteries. All right. So my X values, I'm going to put in L1. My Y values, I'm going to put in L2. So you just put it in and hit enter. Just go all the way down.
You want us to copy your numbers?
Yeah, this is the drilling data. So if you have the PowerPoint, you can just get it off of the drilling data, or you can copy my numbers. I'm trying to go slow enough so that you can copy them. Going back up to my Y values. You should be able to see all but the last one of the X values. The last one's 190.
I can't remember if I asked you this the other day or not. I don't think I did. Um, well, I'll let you finish this. It was a thing on
Go ahead,
the,
I'm listening. Go ahead.
okay, sorry. It was a thing on the homework for chapter 4 and for R2 on my calculator when I figured out the Lin reg, it gave me 0.2888, and so because it wanted it one decimal place, I put 2.9. It was trying to figure out a percent, but then I realized I had to convert it to a percentage, so I needed to times it by 100.
Right.
And so I was so lost for so long, and I kept looking up things, and then I realized what I was doing wrong. And I don't know if I mentioned that last class, but I just wanted to say I figured it out. So
Good.
everything's
Good.
good now.
It's frustrating. One thing that's frustrating about my open math is they jump back and forth between give me a decimal, give me a percent, give me a decimal, give me a percent. And it's really frustrating because you get into a groove of doing it one way and then it'll just like throw a random one in there.
Yeah, that was definitely one of those. Thank you.
Yeah. All right. Does anyone need another moment or we all have our numbers in there? We all good? Okay. Now we're going to hit the stat button again. And you go over to calc. So you're going to arrow to the right to calc. And we're going to use number 4. This is Lin Reg AX plus B. So you're going to go down to number 4 and hit enter. So you should have this screen. You probably don't if you are on the 83. I believe on 83, it's just going to say Lin Reg and have an open parenthesis, So what we need is we need our X list to be L1. If you don't have anything in there or you have something weird in there, or if you're on a TI 83, you just hit second 1 to get L1 in there. Then go down to Y list. My Y list is in L2. If you're on the 83, if you don't have this screen, you'll put a comma between them. And then I'll hit second 2 to get L2. Now, if you were using L3 and L4, then your X list would be L3 and your Y list would be L4. Wherever you put them, whatever list you put them in, this is your X list is that number there, Y list is there. Because notice down here, I frequently use like all 6 of my lists. L1 is second 1. You see the blue right here. So whichever list you're using, it's just second and then that number. All right. We're leaving alone frequency list. We're leaving alone store reg EQ. Going down to calculate. If you're on the 83, I believe you just need to close your parentheses. And I'm going to hit enter. Right, you should have this screen. Do we have the same numbers? Okay. All right. So what this is it's a linear regression. It gives us the equation of the line, that is the least squared regression line or line of best fit. So what the line is it's the line that fits our data the best. Now, how well it fits the data depends on how strong of a linear relation we have. So that the strength of the linear relation is going to be that this is a really good line, or it kind of sort of fits our data. So our R value, this right here, our correlation coefficient, we have 0.77 is our R value. I'm going to write it down real quick here. So when I go back to the next screen. So the 0.77, it's pretty moderate. You could say moderately strong, or you could just say it's moderate. Um, statisticians love adverbs, so we say things like moderately strong or relatively strong. This is now if you're building a space shuttle, this is not a good correlation coefficient at all. If you are putting a garden in your backyard, it's not terrible. So our R value, I would probably call it moderately strong. So that's probably where I would go with that. The R squared value, we're not going to be using R squared value a lot. It's going to ask you for it, but it's not going to really ask you to interpret it because it's kind of confusing. I will tell you what it means, and then you're just going to find it when you're told to find it and not use it for anything. So what R squared is, it's called a coefficient of determination. You don't have to memorize that. What it is telling me is that 59.7% of the variation in the Y value can be explained by this equation that we come up with. So 59.7% of the variation in the distance of the ball, or no, wait, this is the drilling, sorry. I lied to you. This is the drilling, not the club head speed. So 59.7% of the time to the variation in the time to drill can be explained by this equation that we come up with. Okay. I'm going to write the equation down so that you can kind of compare it, even though I think a slide later tells us to write it. So this is y equals mx plus b. Some reason they use a. This a right here is the slope. This b right here is our y-intercept. So I'm going to write the equation down. So it's y equals 0.01155x. I went further than I have to, plus 5.527.
Which one did you say was your slope and your A is?
So A is slope. So A is the m, the slope on y equals mx plus b, and b is your y-intercept. I'm going to pop back over to my slide. So my R value is 0.77, that's the correlation coefficient, and then this is my equation. So with a correlation coefficient of 0.77 and my R squared value of 59 point whatever percent, I probably would not make a whole lot of predictions. I'm not going to predict something beyond the 190 feet. I mean, I could be, if I was predicting like 150 feet deep, how long it would take to drill, it might be all kind of accurate, but not super accurate. So I'm going to give you my rule of thumb for correlation coefficients right now. So generally, if I had something that is 0.85 or higher, I would call it strong. Now, at 0.85, I might throw in the adverb relatively strong. Anything above 0.9, obviously, that's just strong. But 0.85 or higher, I'm going to call that strong. So at about 0.65 to 0.84, I'm going to call this moderate. I would probably, as I get to 0.75 and up, I might say moderately strong. No one's going to get mad at you for saying moderately strong or moderately weak or any of that. Nobody's going to get mad at you for that. But I'm going to start getting to the moderately weak when I get to about 0.45 to about 0.64. I would probably call this moderately weak. and about 0.3 to 0.44. I'm just going to call this weak. Whoa, that's not, I'm going to call this weak. And then below 3, below 0.3, I'm going to say it's either extremely weak or basically no correlation or, you know, anything like that. So below 0 point and then below it, this is like very weak. That weak down to no correlation. Now, I'm not going to get mad at you. If you decide that 0.8 is strong, I'm not going to get mad at you. I'm not going to mark you down for it. But if you told me 0.3 was strong, I would mark you down for it. There's wiggle room in all of these. This is just kind of a rule of thumb to just kind of give you an idea. This is not like the rule. There is no rule. So this is just kind of gives you an idea. But if you told me, if you had 0.15 and you told me that that was moderately strong, I would mark you down for it. But if you said that 0.75 is moderately strong, I'm not going to get mad at you.
It makes me think of like the average grading scale, like for A's, B's, D's, just like for the school, because it's pretty much, I mean, like average and then high and then low.
Yeah, I mean that's a real kind of a great way to think of it. I mean, it's kind of almost like a grading scale with a curve because strong goes down to 0.85. So just think about it with a little curve there. So, yeah, I like it. If that helps you to remember it, that's what you do. Definitely. Is that clear as mud? We're good? Do you guys want me to leave this for a second so you can write it down? Okay. All right. So I would like you to put in these ones. These are the club head speed. I'm not even going to put this in my fancy schmancy on my screen. I'm going to use my handheld one. I would like you to put these in your L1 and your L2, and I want you to find the correlation coefficient. Now I'm going to put them in my own handheld calculator. Of course, my handheld calculator that I didn't do the diagnostic on, so I have no R value. Put the buttons. So it's at stat, calc. It's number 4, lin reg, AX plus B. That's where you're going. Go ahead and compare yours to mine once you're there.
I figured out also on the calculator, if you mess up with like not adding a number, you can hit second and the INS and it'll insert like a zero. So you can, I know that's confusing, but it helped me out a couple times when I didn't want to have to restart the entire list. I just missed one number when I was double checking.
Trust me, that insert comes in really handy. I'm gonna pop over so to show what you're saying because it's really amazing. So I'm gonna go to stat and edit, and I'm just gonna insert a line. Let's see. Let's say right here I messed up. So I'm gonna do second insert, and notice it just inserts a zero right above where I was. And then I could type in whatever number I missed. And I'm gonna see if I can delete it now. Yes. And if you hit the button without second, it's delete, and it'll delete one of the numbers. So yeah, so if you miss one, that's awesome. This calculator does so much. So if you have a TI-84 also, I see except a couple of you still working real quick. Do you guys know about copy and paste? If you have the TI-84, like I'm just going to put something weird here. Okay, so let's say I wanted to reuse this thing right here. If I arrow up and highlight it, if I hit enter, it's going to paste it in there. And then I can add things to it or change a number or whatever. Not all of them do it, but most of the TI-84s will. So you can check and see if yours does. It's really cool. All right. So how did we do on finding the correlation coefficient? So I wrote the R squared value down because I want to talk about the equation. So the R squared value is telling me that 88% of the variation in the distance can be explained by the equation. So if I write this equation right here, y equals the A value, remember, is your slope. And then the B is your y-intercept. Okay, so 88% of the variation in the distance can be explained by this equation. So what this means is that we can use this to make predictions. I wouldn't go too far out. I would not say, let's check out 150 miles per hour. You don't want to go too far away from your data set, but I'd feel pretty confident going to like 109 miles per hour. That's not that far away from our data set. Because I have a correlation coefficient, take a look here, 0.94. We all can agree 0.94 is strong, right? I don't even really need any adverbs there. 0.94 is pretty strong. So I can feel confident that I'm going to get a pretty accurate number using my equation. Using this equation back here, I'm not going to feel as confident because it was like 58% of the time to drill can be explained by the equation. That's not very strong. I'm not gonna say with confidence at 135 feet down, it's gonna be exactly this. I'm not gonna feel super confident about that. I'm gonna feel pretty confident here.
So in the last equation, there was a plus. In this one, there's a minus. Is that due to negative or is that?
So my y-intercept is negative. So most of the time when we run these, our y-intercept is pretty meaningless. So what this is saying is if at a 0 miles per hour club head speed, it's going to go negative 55.797 yards. Makes no sense at all. If I don't move my club, it's going to roll backwards 55 feet. It makes no sense. Most of the time they don't. This one right here, this might be actually. This one is saying if I start drilling at 0 feet, it's going to take me 5.5 minutes. That could be accurate. It's just kind of, you got to kind of use common sense, because it
Okay.
doesn't make sense to not swing your club and have it go 55 feet backwards. A lot of times you have to kind of think, okay, I need to restrict my domain. I need to figure out what value am I going to start taking this seriously. So I probably wouldn't for like less than 90 because that's not too far from our data set. I'd say, okay, at 90 miles per hour, that's when we're going to start taking the data seriously. That makes sense. Okay. Other questions before we move on? Because we're almost out of slides. We're almost done.
I noticed that when you're writing the equation, you're not rounding. It's important to use as many decimal points as the computer give or the calculator gives you.
I'll usually go 3 or 4 decimals out just to kind of be safe. Because the more decimals you use, the more accurate you're going to be. You're going to get more accuracy with less rounding. So I usually go 3 or 4 decimals out. There's not a rule there either. It's just what I do. But our value is standard to be 2 decimal places. So it's pretty standard just to stick to 2 on the R value, unless if my open math tells you something different, listen to them. But generally we go to 2. All right.
I have a question really quick.
Yes.
If the R value is the correlation coefficient, right?
Mhm.
What is the R squared again?
It's called the coefficient of determination. I will write it down.
Okay.
And I don't think you're going to see it written anywhere. It might be in your book. It's probably in your book. And they don't ask you to interpret it so much in your homework. I just feel like I want to tell you guys what it means because I find it interesting, but it can be a little bit confusing. I feel,
Gotcha.
yeah, I think the homework just says what's the R squared value. I don't think it actually makes you interpret it. I think it's interesting, so I give it to you.
All right, thank you.
Uh-huh. All right. Anyone else before we move on? All right. So correlation doesn't equal causation. When we have an observational study, you cannot conclude that there's a causal relationship. Even though I'm this one right here, I think that we can say that the club head speed probably causes that distance. Observational studies, though, you can't say one thing causes the other. So, for example, there is a correlation between teenage birth rate and homicide rate since 1993. It's 0.9987. That is almost a perfect linear relationship. However, you cannot conclude that the higher teenage birth rate causes higher homicide rate. This data is observational. You can't conclude that. People will try to conclude that, and it's really fun to say to people correlation doesn't equal causation. And I'm going to give you some really great examples because I always like to take a couple minutes. Nobody's ever been mad at me for taking a couple minutes for this. Let's see here. Spurious correlation. This is one of my favorite websites because I'm a weirdo. This website gives you things that have high R values that don't really have anything to do with each other. Like right here. Like popularity of the first name Walker correlates with Old Dominion Freight Line stock price. My R value is 0.992. There's some really funny ones in here. Let's see here. UFO sightings in New Mexico correlates with patents granted in the US. R value of 0.937. Here we go. Associate degrees awarded in music and dance correlates with solar power generated in Costa Rica. 0.988. First name Aubrey and Exxon's mobile stock prices. That's a pretty good one. U.S. household spending on processed fruits correlates with GMO use in cotton in Louisiana. That's 0.926. Air pollution in Des Moines and number of postmasters in Iowa. This one's 0.891, still pretty strong though. There's a ton of them. There's hundreds and hundreds. This one's good. I like this one though. Biomass power generated in the Philippines correlates with Google searches for avocado toast. 0.977. So see, correlation doesn't equal causation, but it's really fun. So there's hundreds of them. I'll write the website down because you might want to play with them. And there's even a spot on this website where you can make your own. And they're fun. Okay. This is tylervigan.com. Or you can just Google spurious correlations. So I actually have a whole book of these. He actually wrote a book, and I have the whole book of them. It's just fun. It's just a fun place to play. So
Some of them are identical. It's so weird. I mean, I know they don't have any reason to like they don't, but it's funny.
yeah, I've spent way too much time on that website. Way too much time on that website. And there's a ton of them that have to do with margarine, and I don't know why, but it's just hilarious. All right. There we go. I'm moving on. Okay. So there's something called a lurking variable that you need to be aware of. And when you are doing your final project, I know I keep mentioning this, you guys are like, you haven't even given it to us yet. Anyway, so when there's not a variable that is not included in your explanatory or your response, but it affects both things, it can be a lurking variable. You can think that there's a strong relationship between two things because there's one variable that affects both of them. So that one variable that affects both of them makes it look like those two things are connected. For example, air conditioning bills increase at this as crime rate increases. So, or as air conditioning bills go up, crime rates also go up. If we turn off our air conditioners, it's not going to make the crime rate go down. The lurking variable is air temperature. Air temperature affects both those things, so they're going to correlate. So that's just a lurking variable. And so be aware of that when you are, when you're looking at other people's data and when you're collecting your own. And none of the homework or anything's going to ask you about lurking variables. This is just one of those, hey, pay attention to this when you're out there looking at people's data and saying, hey, that doesn't make sense. There's something missing there. All right. So we've already kind of done this, and so we're going to go through this fast, but there's the least squared regression line is also called the line of best fit. I'd usually just call it a line of best fit, but the official term is least squared regression line. So it is the line that goes through the data that best fits the data. It minimizes the vertical distance between the data points and the line. So it's just the best estimate. And that's the line that we already found. So this tells us to find it, but we already did. So going back here, this line right here is the least squared regression line. It is the line of best fit. It is the line that best fits our data so that we can use that to make predictions. Same thing on the next one, this one. That's the line of best fit. It best fits our data. And we're going to be using Excel in a minute to create a line of best fit.
So it changes between A and B, the line of best fit, because I wasn't the last one, the 5.527 was the line of best fit, and this one's the A. Does that make sense?
Uh-uh.
So
Least squared regression line and line of best fit are the same thing. So it's just the y equals ax plus b.
okay, the whole line is the line of best
Yes,
fit.
yes, sorry. I didn't mean to point to the number. It's the whole.
That's what I was thinking. Okay,
Sorry
sorry.
about that.
No, you're okay.
Yeah, the whole line is the line of best fit. Yeah, I just pointed to two different places. Sorry about that. I can see how that would mess you up. Sorry about that.
You're okay.
All right. So we already found these lines, so I'm going to go right past those. And that's the last of that is the last slide. So I actually think as far as visualizing what's happening, I feel like the our lab on this one helps understand the data, or it helps understand the content better than just about anything else that any other lab that we do. This one is a really good one for that. So before we move on to the lab, does anyone have questions?
I had a question about the last lab.
Uh-huh.
So on question 4, it was talking about like if it's skewed or if it's bell-shaped.
Uh-huh.
And my median and mean were 0.25 apart. So I was wondering if that's close enough to be considered bell-shaped or if that would still be skewed.
Absolutely bell-shaped. It's
Okay.
super close. Yeah. If they're, remember, we don't deal in absolutes. So if you think it's super close, it's super close. Now, if they were like 3 apart or something, I probably, unless your numbers are in the 10,000s, you're just kind of use your best guess. If they're pretty close, call them pretty close.
Okay, thank you.
So I have a quick question.
Okay.
So if it says find the least squares regression line,
Mhm.
you actually put in the equation mx plus b. Like it's the
Yes.
whole equation for that answer?
Yes. So it would
Okay.
be this whole thing right here, this whole y equals all of that. That is the least squared regression line right there.
Okay.
All right.
Okay. Thank you.
Uh-huh. Anyone else? It looks like,
Can you repeat what you just said? I was distracted. That was the answer to her question. Yes, that whole equation.
yes. Yeah, the whole equation is the least squared regression line. I see that my things are moving slower. I don't know if you all are getting the delay that I'm getting. I'm looking at my other computer and it's like delayed a little bit, moving around. Okay. So we are now going to jump to the lab. So if you have your lab up and you want to go move along with me, go ahead and give it a second because it's not showing up on my other screen yet. Okay. My goodness. Are you guys getting a lag in your video or is it just me? Yes, lag. Okay. I'm gonna unplug my iPad, so I won't be able to write on the iPad again, but I'm gonna unplug my iPad, hoping that that's gonna help with the lag a little bit. Let me see here. Okay, it's still there a little bit. I'll just try to talk slow. It seems to be a little bit better. Okay. So, this is lab 3. So over here, you're going to have your raw data and you're going to have 2 different variables that look like that you think might be correlated. I made mine up, just letting you know. I totally made them up. So I just took the age of the husband and the age of the wife, and I decided, hey, probably as one person gets older, their spouse is also going to be older, and most likely people are going to marry each other that are close in age. I just decided to randomly do this. Okay. So what we're going to do is we're going to insert a scatter plot and we're going to put a trend line on it and it'll give me an R squared value. So once you have your data in here, I would love it if you would name your variables. Now, the one that's on the left is going to be the X value. The one that's on the right is going to be the Y value. Okay, I'm going to highlight these. I highlighted all my data, and now I'm going to insert. And if you go to recommended charts, it'll probably give you a scatter plot. If it doesn't, this one right down here gives you a scatter plot. You don't want crazy, weird things like this on it. Just choose a regular scatter plot. Here we go. I'm going to move it over here. Let's make it bigger so you can see what's going on. All right, this is my lovely chart. Now I need to add some things onto my chart. So over here, it's add chart element. I want axis titles. Make sure you give me axis titles. I'm going to take care of this before I do anything else. So remember, the one on the left is the X value. So I'm going to put husband's age. And then the one on the right was the wife's age. This is my Y value. And my chart title here is spouse, ages of spouses, I guess. Okay, so on mine, okay. If your X values are in order from smallest to largest, make sure that you still have the Y value that correlates with each one. Like for example, like if I wanted to make mine in order right here, just a second here. So I could highlight all of the husband's ages and then go over to sort and sort from smallest to largest. What this is going to ask you is, do you want to expand the selection or do you want to continue with the current? You want to expand it. I want these also to move, sort, because otherwise what's going to happen is that was weird. What's going to happen is they're not going to be next to each other anymore because I want this 25 to always be by the 22 because this is one married couple. So make sure that you expand the selection if you want to do it like that.
Do
Okay.
you want us to ascend them? That's what I was gonna ask
No,
before
you
we
don't
even
have to
made
do
the
that.
chart.
It's
Okay.
going to do all the work for you.
Oh, okay. Okay, good.
Yeah, so if yours is already smallest to largest, that's fine. Okay. I'm going to come back here. Now the next thing we're going to add, I'm going to go back to my drawing here. Okay. The next thing I want to add is I'm going to add a trend line. So add chart element, go down here to trend line, and I want linear. Okay. But what I also need, just a second here. What I also need on my trend line, just a second here. There's my data. Okay. You want to display the equation on the chart and display the R squared value. So what I did was I just double clicked on the line. When I double clicked on the line, I could get the data right over here. I want the equation and I want the R squared value. You need to have those on there. I'm going to make my font bigger because I can. So you can change your font, you can make it bigger, whatever. There's a few different options here, but we want the R squared value and you want the equation. They will not give you an R value. It doesn't give you an R value, it just gives you R squared. So I'm going to show you how to get the R value. So what I'm going to do, I'm going to put R equals right here, but then I'm going to move over here. Uh-oh, what? R space equals, I want this to be pretty. Over here, I'm going to do math. Remember, equals tells Excel, we're going to do math now. SQRT is square root. Then I'm just going to type in this number, 0.8616. I'm telling it to take the square root of that. Because I have an R squared, I need to take the square root in order to get my R value. There's my R value. Now, when you take the square root, it's always going to give you positive. So you need to pay attention if your slope is negative. So my slope's positive, so it's not an issue. But if your slope is negative, you're going to need to mention when you talk about it down here that it is a negative slope, that it has a negative. So pay attention to if it's negative. All right. Let's talk about what we're going to put here. What's your population? So my population is imaginary Facebook friends. So your population is going to be whatever it could be just the United States. It could be the hospital down the road, whatever your population is. You guys know how to find that by now. Once again, what are your variables? I don't care why you're interested in them. You don't have to be interested. Don't even answer that. What are my variables? My variables are the ages of husbands and wives. My units, they're years. Most likely you're going to have units on one or both of your variables. They could be different units. So just make sure you give me your units. On letter D, on the why are you sure that your two variables have an association? Now, this is basically before you put a trend line on there, why do you think that they are associated? I think people who are taller generally have bigger feet. I think people who are married are usually close to the same age. I think people who are heavier are going to have more rushing yards. I don't know, I'm making stuff up. But Why do you personally think that your two variables are associated? Now, they might not be in the end, but that's what I want to know. How did you get your data? Where'd you get it? All that. Okay. This is the gold right here. This is where the majority of the points on this assignment are your graph and then this question right here. How good the associate, man, that is a terrible question. It's the gold question and it's missing a word. How good is the association between your two variables? I want you to reference your R value and what it means. I would probably say something like, my R value is 0.928, which is a moderately strong positive linear relation. There you go. Or just, it is a strong positive linear relation. Yes. So you're just going to talk about how strong is the linear relation? Is it positive or negative? And then that's it.
I got a phone call literally right as you were showing us the y and the r squared, and I'm so upset about it. Can you re-show me really fast?
Okay, what am I showing you on how to get the R value or?
I know how to get those. Did you just type those in, or was there a way
This is
to?
this is math. I did look up in my bar up here. I typed in equal and square SQRT and then this number for R squared.
No, no. So like on your chart, how it shows the y
Oh,
equals.
this right here?
Yeah.
I just double click on the line after you.
Okay.
Did you see how to insert the trend line?
Yes, I
Okay.
did see that.
Double click on your line and then go up to here to data, to the little bars.
Okay.
Display equation on chart, display R squared value on chart.
Oh, okay.
Yeah,
Awesome. Thank you.
you're welcome. All right. Anyone else? This is basically it. I'm basically done with the lab. Anything else? Any other questions on the lab? Just letting you know, this is my favorite lab of the whole term. It's my favorite one. It really, really is. I'm not going to say that about the other ones. This is really my favorite. Will this be on YouTube? Yes, I will. I'll put this. This is on the end of our Zoom meeting. And plus there's a if you hold on a second here, get back here. If you go to the content down here in week 3 materials, down here, how to do lab 3, there's a video right here on how to do lab 3. There's also lab 2 instructions if you haven't gone there already. But how to do lab 3, there's a video right there. And then plus this is on the end of this week's Zoom meeting. It'll be there. All right. Any other questions for while we are recording?
Was there a test prep other than the practice test that actually covers content?
There is that test review on, if you click on the chapter 3 continue in section 4.1, if you go down here at the very bottom, there's a test review right here. And then also you can still access all of your old homeworks. It's just for practice. So I could go into any of the old ones that are past due and you can practice them as many times as you want. You don't get credit, obviously, but you can just practice any kind of problems that you need to practice. Right. Any other questions for while we're recording?
Is Tuesday the day that we can pop in with questions about the test review?
That
And
was
then
a great
after that,
question.
take the
Yes. Tuesday, we will not have regular content. From 5:30 to 6:30, I will be in here for drop-in office hours. So you can just drop in and ask questions. I'll sit here with my trusty iPad and my calculator and answer any questions on the test review or any other things that you guys have questions with. The test will open at 5 a.m. on Tuesday. It'll close at 11:59 on Thursday. I highly, highly recommend take the practice test early enough, long enough before you take the test for me to be able to troubleshoot anything that might go wrong. So taking it now or taking it over the weekend is a really great idea. Don't try to take the practice test immediately before taking the test. That way I can troubleshoot anything that's going wrong with the respondus. It's pretty rare, I have maybe one person every other term that has an issue, but inevitably, if you're taking it at 9 o'clock at night right before you take the test, and I can't help you, that's when there's going to be a problem. So take the practice test ahead of time, please, please, please. Okay. Anything else for the video for while we're recording? Okay, I'm going to unrecord.